Okay, so let's start for today. Today we'll be covering two mathematical topics rather than like today's discussion is more on building your math skill set for the upcoming 2 weeks. So we'll discuss the second order differential equation and we'll discuss some like concepts from linear algebra. So what is the second order differential equation and where does it become important in this context? So in our context, in engineering's context, we start with a mass spring damper system, or let's start with a simple mass spring system. If this was its initial position and you disturb it by some initial position, like this was its neutral position where the spring force was 0, and then you disturb it by some position x naught, or let's say x, then according to Newton's second law, you go ahead and write down F equals ma. So when you go ahead and write down the second equation of like second law of motion, then the forces on the mass are basically negative kx, and the acceleration is given by d2x by dt2, which I'm going to denote by dx double dot. Okay, which means that the differential equation, when we write down the equations of motion, it comes out to be a differential equation which we need to solve. And since this involves a derivative of the second order, how many pieces of information do we need to solve this equation completely? We need two more pieces of information, as in boundary conditions or initial conditions. So here we will be having some initial conditions like x at the rate time t equals to 0 was some x naught, and x dot, that is the velocity at time t equals to 0, is 0, which means that you kind of pull the mass to some position x naught and then release it from 0 velocity. So we go ahead and guess the solution. As you might have, you can either do it by Laplace transform or you can do it by guessing the solution. I guess that taking an ansatz is the thing that a lot of you would be familiar with. So you go ahead and write down sine omega t plus b cos omega t, where omega is root over k by m, and then you need to go ahead and find out these arbitrary constants a and b, which can be done by substituting x at t equals 0 was x naught, which comes out to be b, and x dot at t equals 0, which was 0, comes out to be omega a, which means that a is 0. So my solution turns out to be x as a function of time t completely as x naught cos root over k by m t. Right? Now you would want this is a pure oscillatory solution, as in how does the displacement look like with time? The displacement looks like you start with some initial x naught and you keep oscillating like this. Now the problem is that when we were studying pitching moment and we had not considered stability derivatives, you would have observed you got an equation something like right? And the problem is that this is purely oscillatory, which means that a disturbance in pitching will make your aircraft keep moving up and down all the time, which is not something that we desire. So we want this behavior to be corrected and brought back to a steady state rather than being oscillatory. So we go ahead and explore one more element to generalize the second order differential equation, and that would be having a spring and a damper. The spring has a constant k, the damper has a constant c, damping constant. So you go ahead and draw the free body diagram of the mass. So this is the force on by the spring, and assuming that the body is moving in this direction, this is the damping force cx dot, or c times the velocity, which means that if I go ahead and write down the second equation of motion, it comes out to be negative kx negative cx dot equals mx double dot, or mx double dot plus Cx dot plus Kx equals 0. We can divide entirely by m so that we can make a general equation which has coefficient 1 with the highest derivative. And then we go ahead and compare it to the standard form of the second differential equation. How it comes into being, you can go ahead and read more in Nelson if you have forgotten how to calculate the solution of differential equations. But if I compare it to the second order expression for a differential equation, actually I shouldn't write omega n. So when we compare this, we find out that it turns out that 2 zeta omega n or 2 zeta omega is c over m and omega is root over k by m, where omega is the natural frequency of the system. Natural frequency as in, if there would have been no damper, then the system once disturbed would have kept oscillating with this frequency. And then we have zeta. Zeta is called the damping ratio. C is called damping coefficient. So now how will you find zeta? Zeta will come out to be C over 2 omega m, which simply turns out to be C over 2 root over. Is this clear to everybody? That if you have a second order differential equation which basically involves a damping term and an oscillation term, then you can find out that what is the natural frequency of the system and what is the damping ratio of the system. Is this clear to everyone? If it's not, let me know. Should I move forward then? Okay. So now our goal is to go ahead and solve this. X double dot 2 zeta omega x dot plus omega square x equals 0. You can do it by ansatz, you can do it by Laplace transform. These things would have been covered in some primary math courses for engineering, so you can go and review them. It's not required for the exam, but you should have the knowledge of how to derive this. So if you take the Laplace transform, then you get s square Laplace transform of x minus s times x dot at 0 minus x at 0 plus 2 zeta omega times s xs minus x at 0 plus omega square xs. Now we need the initial condition. So I told you the initial condition velocity is 0, and we can assume that x naught is also 0. No issues. Because even if I stretch it x naught, I can just change my coordinate frame and bring the origin back to x naught. So just for the sake of simplicity, if I now take x as the constant, which is the Laplace transform of the position, then I get s square plus, and this was also 0, plus 2 zeta omega s plus omega square equals 0. So when can this be 0? Obviously the Laplace transform is not going to be 0 for all distances, all frequencies, which means that this has to be 0. So we need to find out for what values of s are these going to be 0. So for that, you must know that you can use the quadratic formula to get the roots of a quadratic equation. So you go ahead and you write s is equals negative 2 zeta omega plus or minus b square, so that would be 4 zeta square omega square minus 4ac. divided by 2a. A is 1 here. Okay. So now these are my solutions. These are the frequency value solutions. So if I go ahead and simplify this, I would get negative 2 zeta omega plus minus 2 omega root over zeta square minus 1 divided by 2. So if you look closely, you can take out the 2. You can write this as minus zeta omega plus minus. Now I'm going to flip the sign of zeta square minus 1. I'm going to write it as 1 minus zeta square, which means that it would become root under minus 1 times 1 minus zeta square. And root under minus 1 is the complex number iota. So I'm going to pull it out. So you're going to see plus minus iota omega root over 1 minus zeta square, right? So basically now you are being told that you can assume a solution x of t, which is going to be a combination of e to the power plus minus st, whatever solution you have gotten. Like you could have, one would be e to the power st plus b e to the power, like the other root, s1t, s2t. So ultimately what you would get is you would get a solution of the form e to the power minus zeta omega t, and then you would have a e to the power. Basically, if I just take the real part, you can ignore the imaginary part. So it's going to become now the question is, it's going to be, I'm going to leave it as e to the power iota omega root over 1 minus zeta square times t plus b e to the power negative iota omega root over 1 minus zeta square times t. Now see what happens. What was zeta again? Recall that zeta was c divided by 2 root over km. So zeta damping ratio is the ratio of the strength of the damping coefficient to twice the square root of the spring coefficient times the mass. That is the spring action and the inertia versus the damping coefficient magnitude. So now there are three cases. Zeta could be like less than 1, zeta could be equal to 1, and zeta could be greater than 1. When zeta is less than 1, what happens? What happens to root over 1 minus zeta square? It's positive, right? And if something's positive, then we can take its square root very easily, which means that in our solution, we have this decaying term, but we also get these oscillatory terms because it is completely imaginary. Does anyone have a doubt in this? There is, you'd be doing God service if you ask your doubt. It is going to clarify someone else's as well. So I'll give you 5 more seconds.
So do we need a Fourier transform or?
No, this is Laplace transform.
Yeah, but we have frequency domain, right?
Yeah, so the solution has been taken back to the, you need to go and revise Laplace transform, or you need to review how to write the solution to differential equations. You need to understand the second order differential equation very properly. If you don't, then Nelson chapter 4.1 and 4.2 is a good review. It's like 8 pages and you can read it in 40 minutes. It will refresh your memory completely. So remember that like the goal of this discussion is to basically familiarize you and to show you that how you will see these things in the next 2 weeks as you do feedback control and stability augmentation analysis. Okay. So if zeta is less than 1, then we are seeing that xt comes out to be e to the power minus zeta omega t times a cos this frequency omega root over 1 minus zeta square t plus b sine omega root over 1 minus zeta square t, right? So what does this solution look like actually? This solution looks something like, there is oscillation, but it decays with time, and this envelope is given by e to the power minus zeta omega t. So you have oscillations, the imaginary part is still inducing oscillations, but the strength or magnitude of the oscillations is decreasing with time. This is called an underdamped system. Now what happens when zeta is equals to 1? So when zeta is equal to 1, then in that case you have 0, right? Which means that it turns into a constant. There is no oscillation. So xt is simply given as some constant a times e to the power minus zeta omega t. And since zeta is 1, we can simply write it as e to the power negative omega t. So now what happens? What does this output look like? This output does not oscillate at all, and this output would simply look like, oh sorry, why have I, yeah. This output would simply look like this. It's the exponential decay curve. This is called a critically damped system. And then if zeta is greater than 1, then what happens?
Compress.
Compress?
Compress the spring.
No, first follow the exponent math in the exponent. So what's happening here? If zeta is greater than 1,
Not really oscillation.
there will be no oscillation, that's correct.
Yeah.
But now what's going to happen? Overdamped, yes. This is the overdamped system. So now 1 minus zeta square would also become negative, and you would bring out the iota. So it would become real now completely. Iota times iota would give you a negative number. So you would have contributions from like both increasing and decreasing modes. So you will have e to x as a function of t is equal to e to the power minus zeta omega t times a e to the power minus omega root over zeta square minus 1 t plus b e to the power omega root over zeta square minus 1 t. And we say that and we say that for example, it's going to now basically if you look at this, there's going to be a large negative exponent and there is going to be a small negative exponent, but both of them are going to be negative. So you can verify that this becomes a e to the power minus t times zeta omega plus omega times root over zeta square minus 1. So now you can see that this is something larger than zeta omega, but in the negative. And then b e to the power minus t. Now you have zeta omega minus omega times root over zeta square minus 1. So this is also negative, but it is smaller than zeta omega. So both are exponential decays. One is fast, one is slow. Which, like for example, you do realize that e to the power minus 10t and e to the power minus t, which one would grow fast? Like which one would come down to the x-axis faster? No? Okay, let's try something. What happened? Yes. Actually, I should simply use. Wow, this is difficult to use on tab. So this is the graph of e to the power minus x. Now we'll try the graph of e to the power minus 10x. Do you see? We have to start at t equals 0. So forget whatever is happening before 0. What do you see? Which one decays faster? The one with the larger negative exponent. Okay? So there are both kinds of behaviors, and if I would add both of them, you see something like this. It's still decreasing, and the green one is a combination of the both. And in the long run, you can see that the green one almost coincides with the red one. That is the one which decays slowly. So the slower the decay, the more dominant it is going to be later on. So this is called overdamped system, right? So what does this mean? Why are we studying critically damped, overdamped? Why is zeta important? Why is omega important? Because I think you have already, you have done pilot feedback, right? In class. So this is what happens. An aircraft is flying. This is its line of motion. This is alpha. Now let's say suddenly there was a sudden gust. So there was some kind of disturbance. And you'll find out that when you go and write down the complete equation, complete linearized equation, then this also comes out to be something like theta double dot plus some 2 zeta omega n theta plus omega n square theta. The equation will always come out to be of this form. There will be a damping term and there will be a oscillatory term. And recall that what are these? These are your stability derivatives. And these are your force or moment coefficients. Recall why you call Cm alpha pitch stiffness, because it acts as a spring. When you were being introduced to equations of motion, remember that we placed an airplane which was free to pitch inside the wind tunnel, and if you switched on the wind tunnel, there would be a positive pitching moment. The airplane would pitch up, but the elevator would try to bring it back, and we could replace the elevator with a spring that was attached to the base of the wind tunnel. So we would have to design. The customer might tell you, like if Red Bull comes to you and they want to design a sports plane. So it doesn't have to be a very comfortable ride. It can have a lower damping ratio, have any kind of natural frequency that I want. But if I'm designing an airliner for Boeing and it's going to carry over 500 passengers, then obviously I wouldn't want that after a tight gust, my airplane does this before it oscillates and decays. You wouldn't want that. You would want your aircraft to return back in a smooth fashion. So that would be either critically damped or over damped. So people will give you performance parameters that this should be my damping ratio, this should be my natural frequency. And based on that, you are going to analyze how to size the horizontal trim tab or how to size the vertical trim tab. Is this clear? So is the concept of a second order differential equation clear? Okay. Moving on to the next part for today is linear algebra, and basically how eigenvectors, like eigen anything, is related to the state space equation that you are studying. Okay, so I'm pretty sure that by now you have come across x dot equals ax. This is like the first order differential equation, and it's very easy to solve if you have one variable. If you have a vector, if x is a vector, then this becomes matrix exponential, And what's actually happening? That if you wanted to find x, right, at some time instant, let's say at t equals 0, you know what is x naught. So you would go and compute x dot at t equals 0, it would be ax naught. Then x at delta t would be given as x naught plus delta t times x dot at 0, which would be x naught plus delta t ax naught. Then x at 2 delta t would be given as 2 delta t would be given as x at delta t plus delta t x dot at delta t. So x at delta t was already x naught plus delta t ax naught, and then you would multiply this with, and what happens? We get x naught plus 2 times delta t ax naught plus delta t square a square x naught. And if I keep integrating or keep going on to further time steps, you can see that the power of a is going to keep raising. So as the system evolves in time, what's happening? This system matrix A is acting on the state vector, and I get the update value. I multiply it with the time step and update my state vector. So how my state evolves is a result of how the matrix is affecting my state. Is that clear? Does that make sense? Does this picture make sense, that how does a system evolve and what is the role of the system matrix here? That with each time step, you are making an update to the state which is dependent on an operation by a matrix on the state. Okay? So now naturally we ask that if we want to study how does the state vary with time, and we want to understand like where will the state vector go in a certain amount of time, we need to analyze the effect of a matrix on a vector. Okay, so what happens? Let's see what happens when we, so I will take the examples of a few matrices and we'll try to see that what happens when you multiply a vector. So I will take a circle, a unit circle. This does not look like a unit circle. Okay, much better. So let's say I take the first matrix 1 0 0 1, and let's say I take a few vectors on this unit circle, like I mark these. Okay, so this is the vector that denotes this point. What happens when you multiply a 2D vector with this matrix which is given here? Let's call it A. So what happens when you multiply a 2D vector with A? Let's see. So let's multiply A with xy, or rather write it as nothing happens, the vector remains as it is. Okay, so that's the property of the identity matrix. It's called the identity matrix. It leaves the vector unchanged. Now what if this was 2, not 1?
Two will be a scaling factor.
Okay, 2 will be a scaling factor, so this becomes 2. Now if I look at all these points that I had marked, and if I plot them after multiplication with A, what is going to happen to the x coordinate of every vector? So every point that was on the circle represents a vector. You get this part? Is anyone confused about this part? Okay, so you multiply any vector on this unit circle with A, and the output that you see is that the x coordinate of the vector doubles up and the y coordinate remains as it is. So what would happen to this circle after multiplication by A? Yes. So now you see that the y coordinate of every point will still be the same, but the x coordinates have doubled up. So the shape will start to look something like an ellipse. What happened here? You had a shape and it got stretched out. So one of the effects of multiplying a vector with a matrix is the vector getting stretched out. That is, its magnitude changes. It can either get stretched out or it can get contracted. If I had 1 by 2 rather than 2, then the vector would simply get contracted. Now, so identity does not do anything, it leaves the vector unchanged. Multiplication by this matrix makes it stretched out. Have you seen any other effects of matrix vector multiplications? What were you doing in Euler angles? Like when you have a matrix like this, and if I multiply it with x and y, what do I get? I get x cos theta plus y sin theta minus x sin theta plus y cos theta. It's rotation. If you don't see it clearly, then let's go and plot it, no issues. So this is some vector x comma y, which means that this must be x, this must be y. So now we have to find x cos theta plus y sin theta. Okay, the geometric construction is actually lengthy, so I'll pass over that. You can, if you have a curiosity, you can go and check it. But what will happen is, once you multiply, this is the new vector if turned by an angle theta in the positive anti-clockwise direction, and the coordinate of this would be this vector here, x cos theta plus y sin theta, and the y coordinate would be negative x sin theta plus y cos theta. So we have observed that when you multiply a matrix, when you multiply a vector with a matrix, we also say that a matrix has operated on the vector. What can happen? There can be no change if there is an identity matrix. There can be only stretching. There can be only rotation, or there could be a combination of both stretching and rotation. Okay. So what does that mean, stretching and rotation? So it means that if you had a matrix which would take this circle to be to an ellipse like this, then not only the circle got stretched, but it also got rotated. So how do we quantify this? That, now the natural questions arise, that how much stretching, how much rotation, along which direction are you going to stretch, how are the directions going to rotate? To quantify these relationships, we go into eigenvalues and eigendirections. Okay, and I would like you to carry the concept of eigenvectors as eigendirections rather than vectors. Why? We'll see in a bit. So the definition of eigenvalue is that it is the solution of the characteristic equation, the characteristic polynomial equation of the matrix. What is the characteristic polynomial equation? So you construct a matrix, lambda is a scalar here, lambda I minus I is an identity matrix, lambda I minus A. The determinant of this thing has to be 0. So if I had a matrix, let's say A equals -1, 3, 2, -5, let's say. Let's see what eigenvalues it has got. We can, without, either we can keep multiplying vectors, we can keep like multiplying it with different vectors and see and observe. That's also one way, right? I could multiply every vector that's there on the unit circle, keep plotting it, and then observe what's happening, but that's going to take a lot of time. So this is the piece of math that you'll have to do a lot of times in the upcoming 2 weeks, so pay attention. So what is this matrix lambda I minus A? So lambda I minus A is nothing but lambda times the identity matrix minus A. So you know the rules of matrix like it's element wise addition and subtraction. So you get lambda plus 1 minus 2 minus 3 lambda plus 5, and you go ahead and try to take its determinant. So the determinant comes out to be lambda I minus A. So determinant is always, like, first of all this minus this multiplied. So you would get lambda plus 1 times lambda plus 5 minus minus 2 times minus 3. So this comes out to be lambda square plus 5 lambda plus 6 minus 6, which is equals lambda square plus 5, and this is 0. Lambda square plus 5 lambda, yeah. So now the definition of eigenvalue is that the roots of this polynomial or the roots of the characteristic equation of the matrix are the eigenvalues of A. And we'll see, like, what do they physically or like geometrically mean in a short while. So what are its roots? Its root will be lambda equals minus 1, lambda plus 5. So its eigenvalues are going to be lambda equals 0 and lambda equals 5. Yes.
Shouldn't the characteristic equation be lambda squared plus 6 lambda plus 5 minus 6?
Oh, yeah, correct. This is going to be lambda square plus 6 lambda plus 5 minus 6. So this comes out to be lambda square plus 6 lambda minus 1. Now you go ahead and find out its roots. So using the quadratic formula, it is minus 6 plus minus root over 36 minus 4ac, so plus 4 divided by 2. So this is 40, and what would be 2 root 10? So minus 6 plus minus 2 root 10 divided by 2, which is minus 6 minus 3 plus minus root over 10. Okay, so just recall right now that we have found the eigenvalues. One of the eigenvalues is, let's call it lambda 1 is minus 3 plus root over 10, and lambda 2 is minus 3 minus root over 10. So for a 2D matrix, we saw that there would be two eigenvalues, and with each eigenvalue an eigendirection is associated. I call it eigendirection, but in the general terminology people call it eigenvector. But don't think of it as a vector, it's just about the direction. So what is this direction? So now you will see that when you multiply, like when we had taken a unit circle, which was the set of, why are we taking the unit circle? Can you guess? Like why do we study the unit circle if you want to study the effects of a matrix? Because the unit circle is the perfect sample space. You have points which are there in every direction, and the magnitude of each vector which points to one point on the circumference of the circle is 1. Okay, so if the matrix expands or contracts it, you can immediately see that. So now what's happening is when you multiply something by a vector by a matrix, let's actually see what's going to. When you are multiplying, let's say, a vector like this with some matrix A, and A has eigendirections v1 and v2 such that the eigenvalue associated with v2 is larger than eigenvalue associated with v1, then after multiplying the vector with first multiplication, the vector will look something like this. Then the vector will look something like this. Then a cubed times the vector will look something like this. A to the power 4th will look something like this. So repeated operations of the matrix on the vector is trying to shift it towards the eigen direction of the matrix. So now do you see the analogy that happens in your first order system update when I was discussing this? So the result of this, if you numerically go and integrate this, then you see that basically at each time step, the effect of A onto the initial state vector, the state vector is being drawn, the initial state vector is being drawn towards the eigendirection of A, and certain components are getting added up, which means that the eigenvalues and eigendirections of A play a role in the evolving, or the how does the solution evolve with time, in which direction does it go. That's why we study eigenvalues and eigendirections. So let's do this concrete example properly, and then I'll show you a MATLAB code. I'll probably try to project something. Where did, yeah. Okay, so if I go ahead and try to find, how do I find the eigenvectors now? So again, remember that you won't be getting vector answers, like you won't be getting 1 comma 2 or 3 comma 4. You would be getting relations among coordinates. Relations among coordinates which define that, okay, this is the direction. Like, how do I, if I tell you that x equals y, does that mean it's a direction or not? No? If I put you on the origin and I ask you, walk on the line that's x equals y, don't you have a direction to walk on?
We do is 1, 1.
The graph which represents y equals x and passes through origin. Are you getting what I'm trying to say? If for a eigenvalue, the eigenvector comes out to be, let's say, 1 comma 1, is 10 comma 10 not an eigenvector? It is also an eigenvector, because I'm telling you, it's called eigenvector, but you keep the concept in your mind as eigendirections. Like, these are the directions along which the matrix is trying to expand or contract. So if you have a positive lambda, basically the matrix, actually, to be honest, what is happening, let's do this example and then I'll give you the complete picture so that we have concrete numbers to feel through that. So if you go ahead and find out, you are going to simply plug this in, lambda I minus a, and we know that this is 0. If you plug in the eigenvalues, right, that is what we found. So if you multiply it with any vector, we are going to get 0, right? So let's plug in lambda 1. So whatever lambda 1 was, I am not going to do the math, but lambda 1 plus 1, and I think this was minus 2, yeah. Minus 2 minus 3 lambda 1 plus 5 times x y equals 0. So if you now to take this together, you would get x times lambda 1 plus 1 minus 2y equals 0, and you would get minus 3x plus y lambda 1 plus 5 equals 0. If you solve both of these, like if you put y equals to y in terms of x using any of these equations, you will actually come to the same solution, one relation between x and y, and that gives you the direction. So in eigendirection, don't think that north and south are different. For an eigendirection, it's a one line, it's one direction. Like north south is one line, right? It's x equals 0. East west is y equals 0. Then something running from southwest to northeast or northeast to southwest would be the y equals x line. Something running from northwest to southeast or reverse would be y equals minus x line. So these are eigendirections. So once you have, let's say, now I got an eigendirection v1 for this, and and I got an eigendirection v2 for this, see what happens. Forget what my matrix was. I have all the information I need regarding my matrix in terms of eigenvectors and eigenvalues. And what happens? Let's say that this was my initial state vector x naught, okay, or some initial vector x naught. and these are the eigen directions of A, V1 and V2. This has eigenvalue lambda 1, this has eigenvalue lambda 2. What actually happens is, you can look at it this way. The important relation is that for an eigenvalue or an eigenvector, this relation holds. That if you multiply A with its any vector along its eigen direction, it's simply going to be its eigenvalue times the eigenvector. That is why we have lambda I minus A times x equals 0. Okay. So now x naught, if I choose my axes as x and y, then I write x naught in terms of x and y axes, right? But what if I choose my axes as v1 and v2? I can still choose them as an axis, and the only thing that I need to know is the projection of x naught onto these eigendirections. So I go ahead and project these onto the, and remember that these projections has to be parallel to the other axes. Okay. So now, okay, so now what is this? This length is x naught dot v2 divided by mod of v2. This is x naught dot v1 divided by mod of v1. Okay. So forget x naught now. We are looking at some vector a1 and some vector a2. And I know that a1 and a2 lie along the eigen directions of A. So what have we learned? That since a1 and a2 are along the eigen directions of A, if I continuously multiply, like if I find out a times a1, capital A times a1, if I go and find out a square times a1, if I go and find out a cube times a1, it's going to be a1 times some constant value, and that constant value is the eigenvalue, right? So what's the eigenvalue associated here? The eigenvalue associated here, let's say, is lambda 1 is negative 3 plus root over 10, and I think root over 10 is going to be slightly larger than 3 but a very small value. So this is going to be positive. So it's a small value, let's say, I don't know, 0.1 or something. So if it's 0.1, so what's happening? A times a1 is equal 0.1 times a1, right? A square times a1 is 0.1 square times a1. A cube times a1 is 0.1 cubed a1, right? So what's happening with each multiplication? So let's say this was a1, and then 0.1 times a1, obviously this is not to scale because you know that it's going to go smaller. So this is going to be 0.1 a1, this is going to be 0.01 a1. So if you keep multiplying, this is what's 0.01 a1, right? And for the other, what's happening? For the other eigenvalue, we had negative 6 point something. So it means that if this was a2, if this was like a2, then you would have, first it would flip sign and go to the other side. You would have negative 6 times a2. Then you would again flip sign, go 36 times. So because it's larger, what's happening? The magnitude keeps getting bigger and bigger, right? And if you have done like, so what will happen? After the first multiplication, your vector is going to be here, and then the negative component is going to be somewhere here. So you travel this, so your x naught a times x naught comes somewhere here. Then next time it will come here and some, now it goes there. So can you see that the one which had the larger eigenvalue, the vector is slowly getting attracted towards that direction, and its magnitude in the other direction is decreasing, and in the direction of the increasing larger eigenvalue it's increasing, right? So this is how the system matrix affects your state. Your system matrix has some natural tendency to shift the system towards its own eigen directions or its own natural frequencies, right? And then you provide some inputs to disturb it, that is b times u, and you go ahead and x dot keeps keep keeps getting updated of because of this continuous application of a onto x. So that is why finding out the trajectory of a linear system x dot equals ax is really finding out what are the eigenvalues, what are the eigendirections, and that completely determines the behavior of the system. Further on, as we do more concrete examples starting next discussion sessions, you will see examples where basically the eigenvalues can be in general complex, but since we will be dealing with real matrices only, the complex eigenvalues will come in pairs. If you have something with a real part is the real part is negative for the eigenvalue, then the system is stable. If it's 0, it's marginally stable. If it's greater than 0, it's unstable. And any non-zero imaginary contribution to eigenvalues means the system is going to oscillate. So this is a very quick overview of second order differential systems and linear algebra. I just wanted to remind you that you are going to use it very much from now on, especially that feedback system. Like I think you have already done feedback control now. So yeah, and then you will have to do, I think, observer design as well. So yeah, review these concepts if you have forgotten about them. I would suggest looking at Nelson 4.1 and 4.2 for second order differential equations. And if you want to review linear algebra, you can go to 3 Blue 1 Brown or Grant Sanderson's channel and just play the introduction to linear algebra playlist. I think it's 10 minutes video, six videos or so. And I don't think so you should need to read a book after that if you have taken a linear algebra course before that. Okay. So yeah, that's all for today.